Welcome back to lesson U1A6, Properties of Vectors. This is video number 3, and we're taking a look at example 6. We're given two vectors in 3D, vectors A and B. You can tell they're in 3D because the coordinates are a set of 3 numbers. And we have to determine the following as indicated. So 4 multiplied by A dot B, for A dot B, and then A dot 4B. So as you can see, we have same terms multiplied but in different orders. So we want to think at this point, so would you get the same answer? So with this in mind, we're going to get to work and we'll find first for A dot B. As you can see, we have brackets around A dot B, and this suggests that we have to find A dot B first. So I'll write the coordinates of A, 3, 4, and 1. Coordinates of B, 5, negative 2, and 3. And I will close the brackets. Remember that when we dot product vectors, we multiply the respective coordinates and we add them at the end. So the x with the x, the y with the y, and the z with the z. So that means that we'll have 3 times 5, which is 15, plus 4 times negative 2, which is negative 8, and 1 times 3, which is 3. So that would equal 4. Now, negative 8 plus 3 is negative 5 plus 15, 10. And 4 times 10 equals 40. Now, let's take a look at 4a dot b. So first, we have to apply the scalar multiplication. And since we're talking about this, I want to clarify with you one very important or two very important definitions that we need to distinguish from one another. So we use the term scalar multiplication when we are multiplying a vector by a scalar. For example, 4 multiplied by a, that's scalar multiplication. And the answer we get is another vector, a vector that has become longer or shorter, depending on the value of the scalar k. So that's what we have referred to as a scalar normally. And the vector that we obtain, it would be longer if k is bigger than 1 or shorter if k is between 0 and 1, or it would go in the opposite direction. So if k is between negative 1 and 0, it will be shorter and opposite to a, and so on. So in scalar product, so not scalar multiplication, but scalar product, so we assume dot product. So it's the same thing as dot product. So in dot product, we multiply two vectors together, and the answer we get is a number or a scalar. So in our case in here, oops, that wasn't supposed to happen. So in our case here, we have the scalar multiplication for a, and then we will apply the dot product. So let's get started. So we have 4 times vector a, 3, 4, 1. And this will dot product the vector b, which has coordinates 5, negative 2, and 3. So this will be the scalar 4 multiplying each and every coordinate. So each and every coordinate will become 4 times bigger. So that means that we have 12, we have 16, and then we have 4, which is dot producting now 5, negative 2, and 3. Again, same idea, same drill. We multiply x with x, we multiply y with y, we multiply z with z, and we all add them all together. So 12 times 5, that's 60. And then we add 16 times negative 2, that's negative 32. And last, we have 4 times 3, which is 12. So add them all together. We negative 32 plus 12, that would be negative 20. Add 60, the answer is 40. So far we're happy with the results. As predicted, we said that the answer should be the same. And so far we got the same answer. Now, in the next question, we'll multiply vector A with a scalar multiple 4b. So that means that we start off with vector A with coordinates 3, 4, 1, and we'll dot product it with 4 vector B. And for vector b is 4, 5, negative 2, 3. That's vector b, right? So we have 3, 4, 1, dot. So again, similar to what we did in the previous example, the scalar 4 will multiply every coordinate. So it will produce a vector with coordinates 4 times as big. So then we have 20, negative 8, and 12. Remember that we obtain another vector here, which means that we have to write the answer in a set of 3 coordinates form. So now that we have the vectors, here we go. So now that the vectors are in coordinate form, we can start dot producting. Again, the same drill as always, the x with the x, the y with the y, and the z with the z. So you multiply them. And then at the end, you add them all together. So 3 times 20 is 60. 4 times negative 8, that's negative 32. 1 times 12 is 12. You add them all together. Obviously, again, here goes the first, the second, and the third product, right? And the answer is 40. So again, we get the same answer, 40. So we should be happy. Now, moving on to example number 7. We have 2 vectors, vector A, 2x plus 3y, and vector 6b is negative x plus 5y. And we want to express the vectors x and y in terms of A and B. So here we're going to use some of the skills that we learned in grade, grade 10, probably when we learn systems of equations. Maybe you learned them in grade 9, doesn't really matter. So first I'm going to start off by writing the 2 equations given. So what we have is 2x plus 3y equals vector A. So they're all vectors here. And we have negative x plus 5y equals vector 6b. So as you can see in here, we have x and y and a, so related, and x and y and b. And we want to express x and y in terms of a and b. What that means is that we need to solve for x and y. So we're going to treat the vectors a and b as some constants, and we're going to treat the whole thing as a system of linear equations where we have to solve for x and y. So one thing that I am looking at here is multiplication by 2 of the second equation so that I can solve the system by elimination method. I am allowed to multiply a vector by a scalar, and when I multiply by a scalar, it means that this scalar will multiply every term in the equation. So the equation now will become, the first one won't change obviously, so 2x plus 3y equals vector A, but the second one will become negative 2x minus 10y would equal 12b. And at this point would say that we are ready to eliminate our first variable, which is the variable x, and we'll do this by adding both equations. So we have 2x plus negative 2x, that's 0x. And then we have 3y plus negative 10y, that's negative 7y, equals 1a plus 12b. So as you can see here, we have the y variable only, and we have a relationship between vector y, vector a, and b. So you can isolate vector I by dividing both sides by negative 7, by a scalar of negative 7. We're allowed to do that. So you can look at it as a scalar multiplication by 1 over negative 7 for both sides. So what that means is that now we'll have vector y equal to a plus b over negative 7. And obviously we can put this negative in front if we wish, right? Or you can leave it in the denominator, but normally we'd like to keep the denominators positive. So I would bring this in front. Now that we have the vector y, we can express vector x in terms of a and b by simply using one of the equations. So I'm going to use negative x plus 5y equals 6b. And I will replace y with negative a plus b over 7. So we'll say that negative x minus or plus 5 times negative a plus b over 7 would equal 6b. So we have a little bit of work to do here. It's not too difficult anyways. So we have negative x equals, so we have 6b on the right side, and we're going to bring over the negative 5, which will become positive 5, a plus b over 7. So negative x equals, you want to make the denominators the same on the right side. So 7 and 1 have a common denominator of 7. So we'll multiply by 7 over 7 here. So that will give 42b over 7 plus 5a plus b over 7. Simplify some more, and we'll have negative x equals, we can bring them under the same denominator of 7. So we have 42b plus 5a plus 5b. So 5a plus b will be just a scalar multiplication, right? So arrow symbols, don't forget. So negative x turns out to be 42b plus 5b, that's 37b, and 5a. So I'm going to write 5a first, and then plus 42 plus 5, 47b. Sorry, here we go. And divided by 7. So obviously we need vector x and not negative x. So we'll multiply by negative 1 both sides, which will bring us to vector x being negative 5a plus 47b over 7. And voila, this would be the vector x in terms of a and b. And we already found y in terms of a and b. Thanks for watching, and I will explain the next question in the next video. Bye for now.